Today we're going to talk about adding fractions. You should remember the basics of adding fractions from elementary, junior high school, but I want to emphasize a few things that will be especially important as we move towards purely algebraic fractions. And the first thing that I really want to emphasize is the idea of like natures. If I have two like things added together, I get more of the same. I can add any two things together. For instance, I can add 5 dogs and 4 cats, but what do I have when it's all said and done? Well, I have 5 dogs and I have 4 cats. So there's no simplification to this except to say that it's 5 dogs and 4 cats. But what if I have 2 cows and 3 cows? Like plus like is more the same. Cows plus cows is how many cows? Well, I'd have 5. By the same token, 4x and 3y is already in simplest form. That's all I would say. Simplification is whenever I can give the fewest terms but equal value. That's already the fewest terms I can make. But 3/7 plus 2/7 is 5/7. Like plus like is more the same. And these are sevenths. Now, just to notice, we would usually say 3/7 plus 2/7 equals 5/7. And there's the whole key of addition of fractions right there. Now, the denominator literally means to give name to. So the names of these fractions are all sevenths, and the numerator counts or tells the number of pieces I have. So I have 3 pieces plus 2 pieces is 5 pieces if those pieces are the same type of piece. So what gives it its name, what tells you that they're like nature, is the denominator. So from there, let's talk about rational numbers. Rational numbers are the ratio of 2 integers. The easiest way to think about the integers, they're the count by 1 ticks on the number line. So both positive and negative, but each one away from the other. And they go infinitely in both directions, but a ratio of 2 integers is called a rational number. So obviously 3 to 5 is a ratio. Notice that any whole number could be put over 1, so that's the ratio of 7 to 1. So whole numbers are considered rational, and if it has a negative in front of it, that simply could be the result of a -4 divided by a +3, the ratio of -4 to 3, or the ratio of 4 to -3. So a rational number could be expressed as fractions, decimals, or percentages, and you should know how to make the conversion between any of those forms. Some of them because they're common and you remember them, but there are general principles for how to change fractions, decimals, and percentages. As we get to the particular problems that deal with that, we'll talk about that more. Mathematicians don't like mixed numbers because a mixed number is an integer added to a fraction. So this actually is 2 plus 2/3. But if I would call that 8/3, then instead of being a mixed expression of a whole number plus a fraction, it's now just one simple fraction. It is especially tricky with things like -7 halves. So when I'm sorry, -7.5. When I say and, the and literally means plus. That's not -7.5. That's -7 plus a half makes -6.5. Now I also have to have a parenthesis around the whole thing. So mathematicians do not like mixed numbers. They do not like decimals, fractions, or percentages. They know how to use them, but they don't like that for the best form. The simplest mathematical form for a rational number is the single reduced fraction. So whenever I say express your answers in simplest mathematical form, that's what I mean. So how do you add, subtract fractions? Well, you convert all your fractions to a common denominator. Then you add the tops and you don't change the denominators. When I give this question on a quiz, you can answer. I'll ask, how do you add or subtract fractions? You say LCD, and I'll trust that you remember all the steps in the least common denominator and how to use the least common denominator. Now, every time that I ask you to change the form of a fraction, I always want to see the form of 1. come into play. So when we cancel a fraction, or reduce a fraction rather, we factor in cancel. And the cancellation is when I see something like a 2 over a 2 that has a reduced form. Well, that's awful, isn't it? Cancellation is when I see something like a 2 over a 2 that reduces to a 1, and 1 multiplies are ignored. So that's the cancel a factor cancel, but notice how important it is to see there's a 1 multiplier there. But when I'm adjusting fractions to a larger denominator, to the common denominator, that's not a simplification. I'm actually making it a more complicated fraction, but I'm just trying to get the denominators, the names of the pieces, to be the same. So I adjust each component fraction by a form of 1, and then I add the tops, and I keep the bottoms the same, and I simplify the final answer. So here's a quick little review of that, and that's what I want to emphasize to you. Now, the first thing I do is create a common denominator. The common denominator is the LCM, the least common multiple of all the denominators. Now, on small numbers like this, like you would see in elementary school, the way to do that is to think about the multiples of 6, 6, 12, 18, 24, etc. And think about the multiples of 4, 4, 8, 12, 16, 20, 24. You would notice that there are a lot of numbers that are common in the two lists, but the least common number in both lists is a 12. So that means I want a 12 denominator for my answer. Now, I'm going to multiply by a form of 1, which is any number divided by itself. How do I turn a 4 into a 12? Well, it needs a 3, but I need it in the form of 1, 3 over 3. And how do I turn a 6 into a 12? Well, I need a 6 times 2 to make a 12, but I use a form of 1, 2 over 2. Now, if I multiplied, I would do top times top, 3 times 3 is 9, bottom times bottom is 12, plus top times top is 10, bottom times bottom is 12, and then I would add the two numerators together, and I would have 19 twelfths. 19 is a prime number, so I know that can't be reduced, and that's the simplest form. Now, if you recognize that this and this are both a 12, and you want to, you can just come up above here and write 9, 3 times 3 is 9, plus 5 times 2 is 10, and then come over here and write 19, and you just save yourself a little bit of writing. When you see mixed numbers, you were taught a certain way when you were in elementary school, but in pure algebra, we never deal with the mixed number. We only go to the improper fraction. And you should know that this is 7/6 and that this is 9/4. Remember the old trick? 1 times 6 is 6, 6 plus 1 is 7. What you're actually doing with that is you're saying I have 1 plus 1 over 6, and I could express the 1 as a 6 over 6 plus a 1 over 6, and that's the 7 over 6. By the same token, I could say the 2 and 1/4 is 2 plus 1/4, and I could consider the denominator 4 and multiply by the form of 1, 4 over 4, and it becomes 8/4 plus 1/4 is 9/4. That's the technical thing of what you're doing. However, you might remember 2 times 4 is 8, 8 plus 1 is 9. There's the 2 times 4 is 8. There's the 8 plus 1 is 9, 9/4. Now, notice again, this is just the same 6 and 4 we had previously. So we have a 12 denominator. And so we just need a 2 over 2 multiplier here to create the 12 denominator. We need a 3 over 3 denominator here to create the 12 denominator. And if you want to show this, then we'd go ahead and say that this is 14 twelfths and this is 27 twelfths. And when we add those together, we get 41 twelfths. But again, if you do this and you want to go back and say, well, this is a 14 and this is a 27, and 14 plus 27 is 41, same thing. So let's talk about some algebraic fractions now. Now, the best way to choose this is to write all the factors in their simplest form and put them in column form. So the only factor I have on this first fraction is an x. But all the factors I have on the 4x are a 2 times a 2 times an x. So I'm going to go ahead and break it down to a 2 times a 2 times an x. And what I see is that both of these lists have an x in common, but the common denominator, or the least common multiple, would actually be a 2 times a 2 times an x. And one of the things to remember is that the common denominator has all the other denominators hidden inside of it. So a 4x here has a simple x hidden inside of it. So that's what I would see if I was just doing it quickly. So the first thing you have to do is to figure out that this common denominator is a 4x. Now notice I don't need to do anything to this first fraction, but how do I turn an x into a 4x? Well, it simply needs a 4 multiplier, but it has to be done as the 1 multiplier, 4 over 4. Now, top times top would be 8 over 4x. Whoops, that's not a plus, that's a minus. Minus 3 over 4x. Common denominator is there, so it simply becomes a 4x denominator. 8 subtract 3 is 5. Now you would have gotten the same result had you come up here and say, well, the 4 times 2 is an 8, and there's no change on the second fraction, so 8 minus 3 is 5. One way or the other, you have to see that all three denominators have to be the same. That is, like plus like is more of the same, and when I add, what they are does not change. How many there are does change. So a little more complicated problem here. This first fraction is a 2 times an x, and the second fraction is a 3 times a y. So I'm putting everything in columns just like I did on the previous problem. But if it's got that term already in it, then I put it in the same column. If not, I make a new column. So 3 times y is 3 times y. So what is it that has all the denominators hidden inside? Well, it takes a 3, it takes a 2, it takes an x, it takes a y. And what you should see is that obviously this has a 3y in it, and obviously this has a 2x in it. But what is that? Well, it's 6xy. So the common denominator will be 6xy. And now I need to simplify my component fraction, or excuse me, I need to adjust my component fractions. If you look down here, you can see that to turn a 3y into a 6xy, I need a 2x. That's the advantage of this method here. So it's not just a 2x, it's got to be a 2x over a 2x. And the thing that turns the 2x into the 6y is the 3y. So this one has a 3y over a 3y. So I would multiply 7 times 3y, 21y, over 6xy, plus multiply 5 times 2x, 10x, over 6xy. Now it's not necessary, but the tradition that we use when writing variable expressions is alphabetical order. Notice that I could have called this 6yx down here, and it wouldn't be different. It would just maybe be a little confusing. So as I add 21y plus 10x, most people would write 10x plus 21y. Remember that addition and multiplications can have their order changed, and it won't change the result. So the conventional thing to do with that one is to put it 10x plus 21y. Now, if this could be simplified, I would simplify it, but we'll talk about that more as we get into the pure algebraic fractions later. Over here, the first denominator is an x, the second denominator is an x times an x. So when I line them up in columns, I come down the column and I see that there has to be an x and an x, and you should realize that the x squared has the x hidden inside of it. So the common denominator is an x squared. And I can leave the 3 over x squared alone, but I need to do something that turns an x into an x squared, and all that is simply to multiply by form of 1 x over x. This then gives me 2x, and notice similarly in the previous problem, I like to put things in certain orders. I like number followed by variables in alphabetical order. So instead of calling it x times 2, I'd call that 2x, and denominator x squared plus 3 over x squared. When the denominators are the same, I add and the denominators don't change. The fraction of x squared plus the fraction of x squared is a fraction of x squared. But what do I have on top? Well, 2x plus 3. Can that be simplified? The answer is no. They're not like things. So it's just 2x plus 3. Now, up here, you could recognize right here, that's a 2x and that's a 3. And I need to add them together, so 2x plus 3. You do not need to copy these fractions again like this, like I did right here, because it's really right there. There's my common denominator. An x squared denominator plus an x squared denominator makes an x squared denominator answer. And what do I see on top? Well, I see x times 2, 2x plus 3. So there it is. Now, we understood that to be a 1. And just quickly, just like the example of the conversion of mixed numbers into their improper fractions, I need to multiply this by an 8 over an 8 so that this becomes 40x over 8 plus 3 over 8. And when they both have the 8 denominator, we get an 8 denominator answer. But notice when I add x's to 3's, I can, but what I can't do is to give a single name to that sum. So it remains 40x plus 3. So you'll see problems like that, and I really would like you to concentrate and think about what you're doing. You're trying to create like pieces. That's the creation of the common denominator. And you want to make sure that each fraction is an equivalent form of the original fraction, but with the common denominator. And like plus like is more of the same. So I add the numerators, the tops that tell me how many pieces I have, but the names of the pieces doesn't change. Now, none of these examples that I gave you had a simplification, but watch out because sometimes they will. And if you can simplify, for instance, if you had something like 12 over 9 as a final answer, you could reduce that. But all the examples that you had here didn't have a hidden 1 multiplier inside of them. That's what cancellation is. And so I just got to that point. I asked that question, can I find a number that I can cancel? And you always have to ask that question, but in this case, the answer every time was no. So, adding and subtracting fractions. Now it's your turn.